in polymers. So I will start with the motivation. So the motivation of the work is entanglement of filaments in general in nature. And for example, A is a cartoon representation of the cell, where you have all these filaments outside of the cell nucleus that kind of keep its structure. And then inside the cell nucleus, you have also the chromatin, which is also another filament. All these can get entangled. And the presence of entanglement affects their function and their mechanical properties. I bring your attention also to see, this is a microscopy image of DNA. And you can see, in this case, it's a circular DNA, so it is tying really a knot. But also we have entanglement of really open filaments, like the first case A, but also D textiles. They are threaded fibers that keep our clothes, functional. So they have impacts on mechanical properties, and there are so many other applications like this. So it is natural, therefore, to look at, if we want to. Sorry, I will move one slide back. As I said, the entanglement of these filaments is responsible to a very big degree for their mechanical properties, right? So if you have this woven metallic structure, it can hold a lot of load, and similarly, as I explained, for the cell and DNA. So the first approach to understand the fundamental theory behind and understand the function of these materials is to be able to measure entanglement in those systems. So it is natural to look in knot theory for measures of topological complexity. And as you all know, that knots and links refer to simple closed curves in space, one or many closed curves in space, and there are many functions, let's say, measures of topological complexity that rely on the classifying those different curves in space. And they rely on the notion of topological equivalence, which means that any two curves are equivalent if we can deform one to the other without cutting and pasting. And these are examples of curves that are all shown to be distinct. And there are many functions that can distinguish those. Now, as I mentioned earlier, entanglement in nature isn't necessarily entanglement of ring polymers, entanglement of closed curves. So even if we remove all the physical characteristics of these polymer chains, I will focus on the example of polymers, and we see them as mathematical curves in space, we still cannot apply measures of topological complexity from traditional knot theory because we deal with open curves. So I got these pictures from nice work online, but these, you can imagine, they look as if they are projected, and they are diagrams of both those cases, but we are interested in these. You can imagine those as living in 3 space. So imagine you have these open curves in 3 space. The notion of topological equivalence is actually a problem that the functions, they rely on that notion, because all these curves, they are equivalent. We can deform them without cutting and pasting. So instead of measures that are invariant under motion of the chains, we are, for open knots and links, we are seeking measures of entanglement complexity that would be continuous functions of the chain coordinates in the case of open curve. So the only measure of entanglement that so far, until recently, we had rigorously could be defined for open curves in 3 space was the Gauss linking integral. So the Gauss linking integral, again, it is defined for curves in 3 space because there are ways to measure entanglement of open curves by closing them, or by a method that relies on knotoids that we'll discuss later. But for knotoids are also 2-dimensional objects, so at least they are diagrams. So we have the information of over and under, but they are diagrams. So how about 3 dimensional curves. The only tool we had was a Gauss linking integral. And I will describe a little bit how even with that, it is not obvious in applications that what we measure, what we can measure with a Gauss linking integral is relevant in applications. So we went through a long, and we are still into this research where we are trying to find whether the topological entanglement or geometrical entanglement that the Gauss linking integral measures is relevant in polymer melts and solutions. And I will describe a little bit what is entanglement in those systems. So polymer melts, they are materials with big range of mechanical properties. For example, silly putty is a material that kids play with, and if they can shape it into box, leave it on a table, and it will sit there like a solid for some time. But then if you come sometime later, it will start flowing like a liquid. So this is a dramatic effect where we have a hole in the middle and you can see it flowing. So what is causing this fantastic change in the mechanical properties, and which is responsible for why they are so useful? So many materials like plastics and all these objects, tires for our cars, they are made out of polymers because of this very big range of material properties. So the reason behind those interesting properties that are called viscoelastic, they are between solid and liquid, is believed to be, and shown in experiments, entanglement. What is entanglement in this situation? There we have systems of many curves, and they look like spaghetti, typically people given as an example. But then the polymer chains, due to thermal fluctuations, or if there is a flow, in the solvent, because of the presence of the other chains around them, this is what this image is trying to show, they are constrained in their motion to move actually within a tubular neighborhood. And so they cannot, after some time, once they move around a little bit and the diameter of this tubular neighborhood, after a while they realize that they could actually move along the axis and escape their constraints. So this is what this critical length and time scales, the tube diameter as well as the length of this the axis of this tube, correlate very well with mechanical properties. And they are created, of course, there is no tube really there. It is created by these topological constraints. So in an attempt to try to measure this type of entanglement in polymer systems, what several groups have done, as Kreger in ETH or Theodorou and Zoumanekas in at the National Technical University of Athens, Everairs in Lyon, they have created these algorithms where, by starting with, this is a molecular simulation snapshot of a polymer melt, and this is shown just, it's a snapshot from a particular angle. It is actually a three-dimensional box, which is simulated with periodic boundary conditions. So they start with a configuration like this, where you see that it is not obvious what is entangled with what and how to measure entanglement. And they start deforming it so as to make it thinner and thinner, but respecting the topological constraints, meaning that they don't allow chains to cross through each other. They keep the ends fixed, and they do this deformation until you see in D, we have something that is a little bit more obvious in terms of having these topological constraints. It is more like a network where the contacts between curves become almost nodes. And then from such a configuration, they can measure the number of contacts or the distance between contacts. It turns out that these very discrete, very simple ways to somehow quantify entanglement, they actually have been included in measures, in theories for polymer mechanics. and dynamics, and they have been given relatively successful results. Of course, there's more improvement to that we seek. It's not completely right. So the question that we want to answer is, can tools from knot theory provide information relevant to mechanics? This was something that originally that has been suggested from polymer physicists themselves. Edwards was the first who suggested that maybe we can use tools like the linking number or something like that because entanglement is not just those contacts that we created with that network, right? It is something that has to do with the global conformation of the chains. And but this question remained open for many years because the problem with mathematical measures of entanglement complexity, coming to the beginning of the talk, is how to deal with open curves and how to account for geometry, since the notion of topological equivalence is not necessarily accounting for that. If we imagine the curves as mathematical curves, we often miss that information. Especially when we deal with closed curves, I mean. Okay, so let's go back to the linking number, and so the linking number is defined for two simple curves in space, oriented, and then in any projection we can see one or the other crossing different signs, and we can take the algebraic sum of intercrossings in a diagram. It turns out, so if we do this on a diagram, we know this is a classic linking number. For closed curves, it is topological invariant. It also measures the number of times one curve intersects the surface bounded by the other, if we look for a more three-dimensional explanation of it. And it is a topological invariant, but it is not a very strong one. We know of cases that it misses, since, as we said, it doesn't account for self-entanglement of the curves. Okay, so this is the classical linking number, but actually it was defined from Gauss in the Gauss linking integral. I think you have heard about it in previous talks. And a way to express this integral, to explain what it means, is to see it as the average algebraic sum of crossings over all possible projection directions. That means we have a curve in 3 space, we choose a projection, we get a diagram, we count the classic linking number, and for closed curves that was independent of the projection we chose, so the average was just the linking number. But if we have open curves, if we choose different projections, might give different average half algebraic sum of crossings. So, might give different algebraic sum of crossings. So if we take the average then, this is what the Gauss linking integral is. Now, this definition can be applied to open chains, and it is a continuous function of the chain coordinates, and it is sensitive on the geometry. So it has those nice properties we seek for applications. Here's an example of the calculation. If it is closed, it always has integer values, but when it is open, it gets the values of the linking number, the linking integral, are real numbers. And you can see that intuitively, we can understand them as we understand the linking number of closed curves. As the number increases, we have more linking. And here's an example where they are just a little bit open. And you see the result is almost 1, since they seem to be linking once. So it agrees with our intuition. Another property of the linking number, as we said, it depends on the geometry, and it is an average half algebraic sum of crossings. And even for straight segments, this is giving a non-zero number. You can find projections of even 2 straight edges where they will cross. And so this number, it is a real number which decreases in absolute value as we increase the distance. So this is something good, again, for applications, since we want to see, as things move and evolve in time, to capture how they get closer together. So it is a sort of a topological interaction that gets higher and higher as these two things would move from something like that to something like this, and eventually start getting really linked. Also, you can apply the Gauss linking integral over one curve to measure what we call its height. So it is again a number of sign crossings that times in a way that times a curve turns around itself, and you can see the examples of height for a curve that is unknotted, a curve that has a knot. But there is, of course, as you see with the height, there is all these numbers in between for an open curve that it can attain. And this is something to show how different this is from the information of just looking at topological constraints in the theory of polymers, because this could be, in this case, we could have 6 other chains in both cases linking with this one curve. But if we measure that, just this number from the algorithm that we showed earlier, this is not, it captures different information than the right. Okay, and this is some example that I wanted to show the right, how the right values might change. Okay, so then we said, okay, let's use this now to apply it to polymer melts, like the one we showed in the beginning that was reduced, that was obtained through molecular simulations. But the problem that we face is exactly the fact that these polymer melts, you cannot see them, you cannot see entanglement through a microscope. You have to do molecular simulations. And not only that, they are so big, those systems, that you cannot simulate the entire system. Instead, you use periodic boundary conditions so that you can avoid having boundary effects on the system you simulate. And so this is work I did for my PhD under the supervision of Sofia Lambropoulou and Ken Millett. And so we're looking now at the entanglement that can come up in systems with periodic boundary conditions. You see, these are cartoon representations of, imagine at the central cell would be what you simulate, and then you have the other things around are the copies of the simulation box. This is another way of seeing periodic boundary conditions, because what periodic boundary conditions do is exactly that. When a curve exits from one phase, it re-enters from the other. As a result, when you glue all those things together, they form an infinite basically system. And when you account in the simulations for the dynamics, you have that a monomer here, it interacts with neighbors on this other cube, not only with what is in one cell. So you account for all the surrounding environment with these periodic boundary conditions. Therefore, we have to account for all the surrounding topology too. So we can show that if we focus only on the filaments that exist inside the box, and we wanted to measure entanglement on those, we would miss entanglement information that comes from the fact that these curves go around and they have a more complicated global structure. So that is excluded from the options. So still we want to measure let's say just the pairwise linking number in this system. Since we cannot focus on just one cell, we say, what if we look at the entire system? Well, the entire system is an infinite system, and you have infinite repetitions of things. So again, this doesn't work. We don't want to account for the same thing over and over. So we want somehow to find a minimal measure of complexity that captures all the different topological entanglement in the system, and that retains the basic properties of the linking number, meaning that it is symmetric. If I take linking number of chain I with J, it is the linking number of chain J with I, and that it is a continuous function of the chain coordinates, and that for closed curves, it is a topological invariant as it should. So we said, let's look at the blue and the red curve as one thing. So as we said in the simulation, we did simulate one blue curve that is just connected at the boundary with its other part, and one red curve. But this create an infinite collection of blue and red curves, and we call them free chains, in accordance to what is a free vector, because we have all these different translations. And of course, this is just a two-dimensional cartoon representation. We are dealing with three-dimensional, three-periodic boundary condition systems. So if you want to see it more mathematically, it will be like three torus. So we propose to define a linking number at the level of all blue and all red curves. And so we say that the periodic linking number is the sum of Gauss linking numbers between an image of the blue curves and an image and all the images of the red curve. That means if we choose one image of the blue, say I1, and add all the linking numbers of I1 with all the red curves, that is the periodic linking number. It is shown here. Oh, I'm talking about a 9 knot. It's not shown in the figure. It could be that also the definition is independent of which choice we choose. So I could choose I2 to do the same. It is the same, the result is the same. Also, we can verify that LK periodic linking number of JI is the same. If I take any red image and unfold it and take all its linking with the blue, it is the same number. So it is symmetric. And you must have noticed maybe as I talk that, okay, if we unfold one blue curve, this is the case of closed chains, well, it only links with 3. So what is the big deal? I can just take the linking number of these 3 images, right? But the problem is when we have open curves, which is the case we are most interested in. So if we have open curves, then we have this curve, this blue curve. It is in different relative position with this red curve than what it is with this red curve and that red curve, and actually with any red curve. So that means it will have a different linking number with each one. So we want to account for all of that in this sum of linking numbers, according to our definition. So is our definition valid? So does it make sense to define this? And indeed, we proved that it is an infinite sum. We proved that it converges. It is an infinite sum, I explained, but we proved that it converges. Okay, so we are satisfied with this definition. It has all the nice properties for a linking number in periodic boundary conditions. In a more mathematical sense, for someone who is more interested in that, you can imagine that this definition defines a linking number in the 3 torus using the infinite cover of the 3 torus. Okay, so we have this definition. We say, let's go on to apply it then to polymers and see. We made all this effort for the applications, but does it actually measure anything interesting? We want to convince the polymer physics community that they can use these tools to make advances in polymer physics. So let's see. We start with, and I will go into work that I did in my postdoc with Kemilet and Paul Latzberger. So we say, let's start with some very simple molecules that have very little entanglement. In any mathematical way, they are not entangled, and in any polymer physics way, the entanglement effects would be very minor. The reason for that is because sometimes people find knots in some polymer systems, and the reply from the physics community is that this is a very special case and it doesn't have a big impact. So we want to show here that actually we can measure a gradual entanglement even in very simple systems. So we studied 4 different systems. First is just parallel. So these are the original conformations we started our simulations with. These are actually bead spring models of polymers. And we have 4 weaves. One is just parallel, it starts like this. One is an orthogonal weave. You kind of understand what I mean by looking at it. And W2 is a second version of the first weave. It's just denser. W3 is one that has a little bit more entanglement in the sense that it goes alternating over and under the curves that it meets. So it has conformations like the ones depicted here. So the molecular weight of the chains is approximately the same, but the last two systems are denser than the first two. And now for the simulation, we did it in LAMPS, and it's a program created by the Sandia laboratories. And we used the harmonic bonds and harmonic angles. And so these represent semi-flexible chains. And we use the Lennard-Jones potential and in a Langevin thermostat. So there is no hydrodynamics really. The solvent is just a Brownian motion acting on the monomers. But this is good enough. So it is valid to use that when you are, especially as the systems get denser and denser. Otherwise, missing the hydrodynamic interactions can be important in some cases. But it is a standard way to study polymers. So what we do then is a standard also experiment that can be also done in a laboratory, which is an oscillatory sphere. That means we start with the periodic box. Again, it is a three-dimensional periodic box, but we depict it here just as a two-dimensional. And you start moving it right and left, so as to change this length in this sinusoidal way. And you account for the stress tensor while you do that. So you can do this slowly, or you can do it very fast. So we do it in a range of frequencies of oscillation, and we average the stress tensor over many frequencies of oscillation over many periods at each frequency. What happens then is that as you measure the stress tensor, if the dotted line is the deformation you do, the stress tensor has a phase lag. It doesn't follow the deformation. If it followed the deformation, it would have phase lag 0. That would be representative of a solid material. But if it has a phase lag of pi/2, it would be a liquid material. Instead, what we see for polymers is a response in between solids and liquids. So by doing a least squares fit to the function for the stress tensor, you can find these parameters that tell us how much out of phase. So these have the phase lag inside, and the loss modulus is a number that represents how liquid-like is a material, and the storage modulus how solid-like is a material. So we will be working with these numbers now, the liquid-like loss modulus and solid-like the storage modulus. And so we did those simulations in two cases for each system. One case where we glued, somehow we didn't glue, but we made the system infinite. Let me show you, I'm sorry, I'm moving here. We looked at this case. So we allowed the chains to continue to exit through the box to create these infinite chains. This is the 1K, the infinite, and the open curve. So we did it in both cases for each system. One case is infinite. The other case is really open curves in 3 space. And here is how the systems deform in space. I just show here only parts of the chain. These are infinite chains. And we see some bundling of the chains, which is something that is observed in experiments. And then these are the open chains that you see they deform much more because now they don't have any fixed constraints in there anywhere in the ends. They can attain conformations that are more those of random polymers in a solution. Then we go to the orthogonal weave. And again, these are infinite chains. I just show a part of each one. And this is the open. Now the open, in principle, it could become like the one that we showed earlier, right? It could become more disconnected one from the other. And I remind you that this is not ending here. There is over and under and left and right. So, but we see that now there is entanglement in the curves. They have, the surrounding curves don't allow them to attain the conformations they would prefer. This one is an infinite. I apologize for this curve here. It is just a mistake in the visualization only. This is just a denser representation of the previous width. Again, the global topology of this cannot change. Locally, we see again this bundling happening. And for the open, again, these are now, they could attain any conformation they want, but they are constrained by the presence of the other chains. Subtle differences, but these are what make the differences in the materials. And this is the third width. Again, you cannot see here, there are other curves around each one. I will show you the full image. And the open curves. Again, they have trouble escaping their constraints. Oops, sorry. So this is, I put here the infinite, the infinite system, the periodic system next to each cell that we saw. Earlier, we just showing the images, the unit cells, but this is what the entire systems look like. There is no really a gap here. That was an issue with the visualization. These are just infinite curves. And you see that starting from these systems, here you see there are blobs. The curves cannot, they are actually unentangled with each other, but they somehow have these interactions that keep them from being totally dispersed in space, at least for the time scales we studied. And, but we don't see any entanglement really happening. Instead, here you see there is the systems, and if we were able to look at it from different directions, they form these tubes of connected chains. So they form these infinite tubes. Here we see now that there, if we look again from more directions, you could see that actually they form planes of connected by entanglement. And the third system forms entanglement, more connections between these planes of entanglement. So it is a percolation from 1D to 2D to 3D of entanglement. Okay, so this is just looking at seeing what the systems look like. And here is finally the mechanical measures. So here we have the logarithm of the storage and loss modulus. And this is what happens as we oscillate faster and faster. This is for the infinite systems. The infinite systems, they, as we said, they cannot drastically change their conformations other than, you know, coming a little bit closer together. They cannot disentangle. And what we see in most systems is that the storage modulus is above the loss modulus, so the systems behave more like solids throughout the simulation. This third system, it has several other factors going into it that it is not easy to say the same thing for them. But it is definitely the trend that we see for the other systems that vary in entanglement and density. Okay, this was the infinite systems. Let's see now for the open systems. So the infinite systems behaved more consistently, more like solids. But now the, sorry. Excuse me, is there a question?
No, I think that it's just some
okay,
noise.
Sorry. Okay, sorry for that. I thought there was a question. All right, so let's see the open curves. For the open curves, you see the empty symbols are this liquid-like G2 loss modulus. The solid symbols, the filled symbols, are the solid-like storage modulus. And we see when we do it for slow frequencies, so you deform it but very slowly, the systems behave more like liquids. And then there is a critical frequency after which their behavior changes, and you see the filled symbols over each corresponding, for each system, empty symbol. So we see a transition from solid-like to liquid-like behavior, and this is exactly what we call what is expected for viscoelastic polymers. So we see that even for these systems that are very, their entanglement is minimal, we see there are subtle changes in the storage and loss modulus transition that indicates viscoelasticity. Okay, let's see if we can capture such a small transition. And here we see the mean absolute right of all these systems. And on the y-axis, on the x-axis, we see the loss tangent is actually the ratio of storage and loss modulus. Basically, you can think this x-axis measures how solid-like versus liquid-like a material is, with larger numbers showing a more liquid-like behavior. And we see something that might seem counterintuitive, but because we know the systems it isn't, that the right increases the more liquid-like the material is. The reason for that is that when the system is more liquid-like, when there are not so many topological constraints, then the chains, they can attain their natural conformations, which would be, you can imagine like a random walk. It can turn around to itself, and so it will have a higher right. But when it is entangled with other chains, it cannot escape those conformations, and it is in general to this entangled conformation, it's trapped in an entangled conformation that might be keeping it more spread than its random conformation would be. And we see consistently, these are the data for the slower frequencies that are representative of more equilibrium. We see that the systems are grouped together. The values for each system are grouped together, and they are consistently increasing for the more liquid-like systems. Now for the periodic linking number, we see almost the inverse behavior, that the most liquid-like a system, the smaller the periodic linking number. And of course, we can understand that in the same way that you have more entanglements, you have more tight contacts, the Gauss linking number is sensitive to all these distances and entanglements. So we see that it can, again, group the different materials into different values, and it correlates with the loss tangent. So this might seem obvious the way I presented it, but it is not obvious at all for polymer physicists. That's something that we measure, which is considered for engineers, and I apologize maybe for people in the audience who are engineers, but typically I hear that they think that this is more theoretical and has nothing to do with actual physics. And here we see that indeed it does have to do, and that maybe our goal would be, how can we control the linking or the right of the chains? It could allow us to control the material properties, which would be, of course, a very difficult problem, but very impactful. Okay, so do you have any questions? Okay, so I was thinking, I had another application, but I think I won't go into that because I want to talk about something else. So, okay, I gave you all the motivation and we saw a successful application of the linking number. And now, okay, let's go further. And I will talk now about some work with Kauffman. So let's go back to what are we interested in. And we are interested in entanglement in physical systems. And I particularly want to work with systems of many chains. So as we said before, we did a successful work with a linking number, but this captures up to pairwise entanglement, right? Nothing more. So, and as we mentioned in the beginning of this talk, there are many measures of entanglement for closed curves in 3-space, but how about open curves in 3-space? Well, since 1877, we've had the Gauss linking integral, even though it took us longer to be able to apply it really to open polymer chains. But then, about 10 years or so before, the method of a more rigorous method of closing curves in 3-space, so that one can obtain a knot, was devised, which gives basically the idea is you have an open curve in 3-space. How can you use these tools to measure its complexity? By closing it. So you could just close it with the end-to-end arc, but what Kemilet, Stasiak, and other collaborators did with the dominant knot was they did many closures And then from those closures, they saw which closure did occur the most, which knot type for each closed curve occurred the most. And so the idea was to assign to an open curve a knot type. And so by doing this method, you can get a dominant knot that is a more rigorous way of just approximating a curve, an open curve in 3 space by a closed curve. And then Dimos Goudaroulis, Stasiak, Kauffman, and Sofia Lambropoulou, they defined the dominant notoid approach, which is you can do many projections of a curve on planes, and from that projection you can get a notoid. You can do it for many projections and then see what notoid did you get the most times. And that is approximating a 3 curve by a dominant notoid, which is now you approximate a curve in 3 space by an open knot diagram. So I want to emphasize that to understand the difference with what I'm going to talk about later. The dominant knot and dominant notoid approaches, they approximate a curve in 3 space either by a closed curve or by a diagram. Okay, so now using all these ideas, we found a more rigorous way that actually we can define Jones polynomial and Kauffman bracket polynomial directly from open curves in 3 space. It is not for open curves after we close them. It is not for open curves after we project them only in one projection and get its polynomial. It is for open curves in 3 space. So let's see how we can do it. So I'll start with notoids. So notoids are open-ended knot diagrams. I think you will hear more about that from Neslihan Kumchu next week. They look like this. And these are all different notoids. You can define equivalence of notoids, equivalence of these diagrams using these 3 moves. They look like Reidemeister moves. But you have also a forbidden move. So you cannot do moves that include the endpoints of the curve. Okay, now using this definition of equivalence, we can define the bracket polynomial of a notoid diagram as follows. So we have this relation, we use these relations, and then once we smooth all these crossings, then we result in several states of these diagrams. So still the states now will have endpoints, and sigma is the sum of labels of the state, S is the number of components, and D stands for this expression. And then we can define the normalized bracket polynomial in this way, where WR of K is the right of the notoid diagram K. And this generalizes the Jones polynomial of notoids with this substitution. So this is just for notoids, okay? So you have a notoid that is a diagram, and for that diagram, you can compute the Jones and the Kauffman bracket polynomial. Okay, so what we propose is the following definition. We say, let L denote a curve in 3 space. Using this idea of projections, we say, what if we take the average over all projections of the bracket polynomial? So this is what this says. It is an integral over all vectors in S2 of projections of the curve in the plane with normal vector psi. And we take this, now the projection of the curve is a notoid. You take its bracket polynomial, you integrate over all vectors on the 2 sphere. You divide by the area. So this is now an average of what you have in here is polynomials. And similarly, you can use this definition to do the normalized bracket polynomial, the Jones polynomial. Again, the same idea, you take the projection of the curve, you have the right of the curve in that projection, and you integrate over all possible projection directions. Now, there are the following key properties of this. I will focus on the Jones polynomial of open curves. If the curve L over which you define this polynomial is closed, this this Jones polynomial is the classical Jones polynomial of the closed curve. If you think about it, if you have a closed curve, independent of which projection you choose to compute the Jones polynomial, it is the same. If L is open in 3 space, now what is interesting is that this polynomial, it will now have real coefficients, and it is a continuous function of the chain coordinates. As the chain moves in space, these real coefficients of this polynomial change continuously, are continuous functions of the chain coordinates. Now, another thing to point out here is that this polynomial that we compute, it is not the polynomial of any knot. If it is for a closed curve, for an open curve, sorry, it is not the polynomial of any approximating or corresponding closed curve. And it is not the polynomial of any approximating knotoid or corresponding knotoid. It is a new polynomial only associated with an open curve in 3 space. I can show you here an example that you will recognize as something strange for a polynomial, right? This is, as you can see it now here, polynomials with real coefficients. And you can see these are some snapshots of a polygonal curve where only one edge is moving. And you can see how the coefficients are changing. Here I write the polynomial in the beginning and at the end. So in the beginning it is more open like this, then it tightens the configuration. And for comparison, I have the Kauffman bracket polynomial of the trefoil knot and of the most closest to this representation of the K2.1 knotoid. So you see that this is now a polynomial that is none of these two. And for the Jones polynomial, you can see again here how it changes. And it is a little bit more easy to understand by intuition here what is happening. You see when it is mostly open, this curve like this, then you get very small coefficients in front of the powers of t, and then the constant here is quite high. When you reach this point, these coefficients are higher, while this coefficient is lower. And these coefficients here, they are the coefficients of what is the Jones polynomial of this knotoid. So of course, this is a very simple case. Once we have a longer chain with more edges, it won't be easy to recognize anywhere any coefficients of any particular knotoid or any knot, because these will be all combined, those coefficients. So you won't be able to tell what it is composed by. But you can tell in this example that indeed you tighten a configuration here that looks a lot like a K2.1 knotoid, but in 3 dimensions. In most projections, that's what it will give, K2.1. Okay, so here it is also how it looks, the Jones polynomial. If we were going to plot the polynomial as a function of t, the Jones variable, okay, so the time is actually shown with different colored curves. This t is just the Jones variable. And you see, this is how what is the polynomial, the dotted line is the polynomial of the trefoil knot, while all these other ones, you see, they are the ones of our curve with only 4 edges. With 4 edges, we cannot even make a trefoil knot. But you see that this is going towards, as we would expect, looking more like the trefoil. As it is going to a configuration that can tie the trefoil, you see that it gets close to what would be a K2.1 knotoid also. And these are also the roots of the polynomial for the different time steps. Okay, so these computations that I just showed, of course, how to compute this? You might think an integral over all the sphere. It is difficult, right? You can, of course, choose just 100 projections, as was done for the dominant knotoids approach and dominant knot approach. And for those projections, find what you want and then average the polynomials. So you could do that. Or you could seek for closed forms of the integral. And the reason why I showed the case of 4 edges is because we did find closed forms of the integral. You can look at our paper here. It's also in archive. And I can show you just how it looks like. So the the polynomial, the Jones polynomial of a curve with 4 edges has this form, where the unknown is this probability, this geometric probability, which we find just by the geometry of the curve in 3 space as basically a cross product and dot product expression over some vectors that come from just the geometry of the chain. I could go into that in more detail. I had prepared a few slides, but I think that it's been already 50 minutes that I'm talking, and maybe we could stop here. Before that, I should thank NSF for funding this work, and also the Laboratory of Topology and Dynamics of Novosibirsk State University.
Thank you for a very interesting talk. And please, any questions or comments?
Yeah, I have a question. In your periodic linking number method, did you consider generalizing it in some ways? For example, you could take a component and all the components that meet it as a kind of a link. And instead of taking the sum of the linking numbers, perhaps you could take the Alexander polynomial of that link, or the Jones polynomial of that link.
Yes, definitely.
Does that work?
I have thought of it a few times before, but it was never pressing because I had other urgent work to do. But there are some things that are a little bit trickier in terms of if we did the infinite collection. But if we, as you said, don't make an infinite collection of chains, I think it works, yes, and I'm looking forward actually to using it. And we can do it now that we have the Jones polynomial of open curves. Now it's even more relevant because now we actually want to compute the Jones polynomial for polymer melts, right? So we have these systems with periodic boundary conditions. So it definitely is very interesting to extend it to periodic boundary conditions.
Yeah, it looks to me like your idea of particularly with finite components, if you have a finite component and you look at all the finite components that meet it, then you've extracted a piece of topology of that whole infinite linking that is invariant.
Yes, yes, I want to look down the details. I think definitely, I think it will work, yeah. Thank you very much. That's a great suggestion, and I think that should be our next step.
Well, any more questions? Okay, if there is no questions, so let's thank the speaker for this wonderful talk, and we will meet next week, next Wednesday. And next speaker will be Neslihan Gugumchu.
Thank you, Eleni.
Thank you very much.
Thank you.